AgCl2. Now again, from solubility rules, we learned that's an insoluble solid. The KSP value for that ends up being 1.6. KSP value here is 1.6 times 10 to the negative fifth. And on the chart that I happen to have here, I'm looking right below it, and it's got AgCl as 1.6 times 10 to the negative 10th. So those numbers we worked with in the previous problem must have been fairly close. We had 1.7 times 10 to the negative 10. Same exponent, pretty good results. 1.6 times 10 to the negative fifth. Now, what this tells me, just in comparison to AgCl, is we learned both of these are insoluble. But as a matter of fact, lead chloride is more soluble than silver chloride. Again, silver chloride's number was times 10 to the negative 10th power. So, even though both of these favor the precipitant side, the PbCl is a little more soluble. As a matter of fact, lead chloride is fairly soluble in really, really hot water. Again, these KSP values that we're doing, these are at 25 Celsius. For most substances, as we heat these up, we can cause these to become more soluble. And we'll talk about how we can predict that from a standpoint of Le Chatelier's principle as well. But now we're going to go backward in this particular problem. So I'm giving you KSP, and we're going to go all the way back to what is the gram solubility of this salt. So KSP, 1.6 times 10 to the negative fifth, is equal to, well, we got to write our equilibrium expression for this solid. This one's a little bit different because this one makes Pb++ aqueous ions and 2 Cl- aqueous. And definitely we encounter this issue with coefficients in KSP. Now, if coefficients scare you, the good news is by having nothing over here, mathematically these won't be quite as complex as some of the quadratic formula problems that you might encounter with acid-base, weak acid, weak base equilibrium. It's a little bit easier to work through, but we'll see some coefficients that will give us a little bit of a headache. So the question becomes, what is lead and what is Cl-? Well, the good news is if I'm going to do an ice table here, barely left myself enough room, I don't have to worry about this because it's a solid. And we're talking about these being none and none, so at equilibrium this one's going to be X, but this one is going to be double X because of the coefficient. So we've got X for the Pb to the first, and then watch what happens here. 2X, my value for my chloride ion, but it's to the second power. So when I simplify this, I end up with X times 4X squared. Notice that's 2X quantity squared, and that equals 4X to the third. So I'm now ready to solve that. So 1.6 times 10 to the negative fifth, divide by 4, and then I'm going to take the cube root of that, and I will tell you, sometimes with calculators you can use the math button and you can find that. Some of them will allow you to automatically do roots other than square root, but I also like, taking the cubic root of something is the same thing as raising it to the 1/3 power. So you can just do your caret sign and put in 1/3 or point and add a whole bunch of 3's in there just to quickly get an answer if you wish. And I end up with X is equal to 1.59. Now, what exactly is X? Well, X is my concentration of lead ions in solution, and I said 1.59. Let's try that again. X is equal to 0.0159. What is X? X is the concentration of lead ion in solution. So lead ion's concentration is 0.0159 molar. The chloride ion concentration is double that. So my chloride ion concentration is 0.0318 molar. So if I want the concentrations of ions in solution, there we go. Now, how do I go from that back to the molar solubility of the solid? The easy way to do this is most of the time when you solve for X, you have the molar solubility. Let me explain why that is fact most of the time. All right, because we're looking for how many moles per liter of lead chloride is going to go into solution. So I'm looking for the easy way to do this is something that it's 1 to 1 with. So if I have that, whatever it is 1 to 1 with, the value at equilibrium is the value, numerical value, for my molar solubility of my solid. It's not that I can't do it with this one. I can do it with the chloride ion, but I'm in a 1 to 2 ratio, so I'm going to end up dividing that by 2, same number, when I try to find the molar solubility of the solid. Again, most of the time when you solve this for X, there's very, very few exceptions, most of which you will never encounter. Most of the time when you solve this for X, you get what you have 1 of, because of it being the nature of an X, which is, in fact, the same value that we're going to have here. Now, again, if you did not use 1x there for some odd reason, then you could definitely do things that would mess that up mathematically. But as I said, 99.9% of the time when you solve for x, you get the molar solubility of the solid, with one exception. It's not molarity, because now we're talking about the molar solubility of the solid lead to chloride, so it's 0.0159 moles per liter. If we want to convert that to a gram solubility, all we've got to do is go from moles to grams. The molar mass of PbCl2 is 71, and Pb has a molar mass of 207.2. So I get a total molar mass of 278.2 grams per mole times 0.0159, and I get 4.4, and I believe we were 2 sig figs in the beginning, so let's go back to that, 4.4 grams per liter. Now, in comparison, definitely not 357 grams per liter like we had for sodium chloride. That's why we call sodium chloride aqueous. It's definitely more than 0.0019 grams per liter that we have for silver chloride. As a matter of fact, a lot of times you'll see lead chloride listed in some solubility tables as partially soluble. So again, it's kind of one that's in the middle in terms of solubility. Now, I don't want to go back and have you relearn those. When you learn your chloride rule, all are aqueous except lead, mercury, and silver. That's net ionic equations. That's working problems that way. But now we actually start putting numbers to this, and we get a comparison. How does this compare to NaCl? A whole lot less. How does it compare to AgCl? It's a whole lot more soluble. Alright, I'm going to run through a series of practice problems here dealing with KSP. I did the introduction, did a couple of problems. My advice to you would be to take a look at the question, pause the video, see if you can work it, and then watch the explanation. But anyhow, if the solubility of copper 1 bromide is 2.0 times 10 to the negative 4th moles per liter at 25 Celsius, calculate KSP. So the first step here is going to be to write our equilibrium expression for this, and this is CuBr, copper 1 bromide, solid, at equilibrium with copper 1 ions and bromide ions, 1 and 1, and so therefore KSP equals copper 1 concentration to the first, bromide ion also to the first. Now remember from earlier in the explanation, this is the molar solubility of copper 1 bromide. So we're talking about the salt, CuBr, when we say that. However, if one of these ionizes or dissociates, maybe to not a large degree, that's what KSP is about, but we're going to get 2 times 10 to the negative 4th copper 2 ion concentration. That's now molar, because we're talking about the ion, and the same thing for the bromide, 2 times 10 to the negative 4 there. So my KSP calculation will look like this, 2.0 times 10 to the negative 4 to the first, times 2.0 times 10 to the negative 4 also to the first. KSP equals 4.0 times 10 to the negative 8th. So there is the KSP. So that tells us, that this lies far more heavily to that side. So again, when we learn solubility rules, there are some things that would be classified as insoluble that we don't learn when we're going through those rules. KSP gives us a little bit deeper look into that. Solubility rules are generalizations to get you through double displacement, precipitation reactions, and some things like that. But KSP definitely takes this to a whole new level. Alright, problem number 2. If the KSP for copper 2 iodate is 1.0 times 10 to the negative 7th, calculate the molar solubility and calculate the gram solubility. So now this one's kind of backward from the other. I'm giving you the KSP, but again, we're still going to start by writing our equilibrium equation. Solid at equilibrium with, this one's a little bit different, copper 2 ions and 2 IO3 minus ions. And coefficients, if you're going to have any issues at all or any problems at all with calculations involving these, coefficients are typically where you'll run into the issue, and you'll see that as I go through these next few problems. Haven't dealt with that a whole lot with the problems we've done so far, but you'll see there are some easy math mistakes to make when you're dealing with the coefficients, and you got to read and interpret the problem really carefully when you're working through these. So we're given a KSP, so 1.4 times 10 to the negative 7. So if I call these 0 at equilibrium, this one's going to be x. This one, however, is going to be 2x. So there I've accounted for the coefficient. However, when I set up my KSP problem, some students say, well, you doubly account for the coefficient. That's semi-true because it's 2x. I've accounted for the coefficient. However, it's also to the second power. So I get x times, you got to be careful with this one, 4x squared, or it equals 4x cubed. So I'm now ready to solve that for x. So 1.4 times 10 to the negative 7, divide by 4, and then I'm going to raise it to the 1/3 power, or take the cubic root. And I end up with 0.00327. X equals 0.00327. Alright, now let's interpret that. That is the molarity of copper at equilibrium, and the good news is if I want to correlate that back to the salt, it's a 1-to-1 ratio, so typically when you solve for x, most of the time, x will end up being the molar solubility, but always check that. Is it something that's 1-to-1? Because you could set the problem up incorrectly and still go ahead and fix that, finding the molar solubility in the end. I didn't ask for it, but if I wanted the concentration of iodate ions, it's going to be 2 times x, because it's 2x once it reaches equilibrium. Alright, so that is my molar solubility. So reporting that answer, 3.3 times 10 to the negative 3rd moles per liter, molar solubility. And then if I want to convert that from a molar solubility, 0.00327 moles per liter. If I want to go moles to grams, all I got to do is get a couple of molar masses. The copper molar mass is 63.55, plus we've got iodine, 126.9. We got 2 of those. And ultimately, we've got 6 total oxygens. So I'm going to add 6 times 16 for the oxygens to get that total mass, 413.35. So 413.35 grams to the mole times 0.00327. And I get 1.4 grams per liter for this one, for its gram solubility. So we got 2 answers here. We got a gram solubility, and then here we have the molar solubility.